Okay, so let's begin. Am I audible, by the way? Can anyone confirm who has joined? Mani Kandan, can you please confirm whether I am audible? Okay, so I think only one person has joined. Actually, what happened that due to okay, just let me have- okay, let's wait for 3-4 minutes and see if somebody else joins. Then we can start. So, due to some unavoidable circumstances, we have been moving from Zoom to Google Meet platform. So from now on, the link will be this for the remaining. This is fourth and remaining 8 sessions. The meeting link will be this one. Whatever you have received of this Gmeet link, right? Google Meet link. And also due to some network maintenance issues, I think the previous session was not could not be occurred this week, and it will be rescheduled. Okay, and you will get informed. So now it's 5:02. Let's wait for 5:05 till 5:05, and then we can start. Okay. Okay. So let's begin. I think the usual attendees are already present. So welcome everyone. This is NOC EE-91 NPTEL tutorial on semiconductor devices and circuits. The course is offered by Professor Sanjeev Sambandhan from IIT Bangalore. I am Debashish Nandi and I am a TA from IIT Kanpur assigned to this course. Okay. As you know, we go live every week from 5 to 7. So stay tuned. An announcement for those folks who have joined late that we have moved from the Zoom platform to Google Meet. Okay, so the link you have received this week, it will continue for the next this and next 8 lectures. Okay, so yeah. So again, let me reiterate some prerequisites that it is expected that you have at least gone through the previous week lectures diligently, which have been posted on the course web page. because I found in last 3 weeks that the except from the initial week, all in for last 2 weeks you were not very thorough about the lectures. Okay, so I had to explain some of the theory concepts again, which I will try to refrain from doing henceforth. So I will request you to please at least go through the lectures before joining these sessions. It will be immensely helpful to you because of twofold reasons. First, that you will be able to understand whatever is being discussed in these sessions, and also you can ask your doubts. Okay. So what decorum you should follow, that please be muted all the time until unless I'm asking some questions, and let us be an informal sessions. It is completely okay if you cannot answer correctly. The attempting is the main issue, right? Attempting the to answer will help you in future, okay, to get your confidence high. Okay, so don't think that if you don't know the correct answer you should not try. At least think logically and try to attempt the answers. Okay, and also at the end of the second hour I'll try to assign 10 minutes for you to ask general query regarding the session. Okay, and also please keep a calculator handy. I saw that last week that some of you were not following the calculations properly. So yeah, so let's begin. This is week 4. So I will start with the leftovers from last week's discussion. Okay, so let's begin. We ended up at the question number 6. So let's start with question number 7. So assume that two semiconductors A and B have same effective density of states, both at the conduction band edge and the valence band edge. Okay, just to know that you are following the sessions carefully, may I ask you anyone if you can unmute and tell me that what is the exact density of state at the conduction band edge or valence band edge? Electrons for electrons in conduction band edge and for holes at valence band edge. Can anyone comment?
0,
0, right?
because
So
f of e is 0.
because not f of e is 0, because g of e is 0, right? I have discussed that the it is like your g of e or the density of states is proportional to root over e minus ec. Okay, so if you put e equal to ec, it this your whatever the proportionality constant may be, g of ec would be 0. Okay, at this point, but again that we consider here only the effective density of states, because when you multiply it with the Fermi function, this area gives you the total number of total concentration of the electron. Okay, so this is very close to this conduction band edge, right? So this thing you should not forget. Okay, so what is given is that uh, two semiconductors are there, A and B. So NCA equal to NCB and your NVA equal to NVB. Fine. And it is given that the intrinsic carrier concentration of A and B are given. Okay. So is the band gap of one semiconductor is given. We needed to find out for B. Okay. So how do we do this? We know that intrinsic carrier concentration for, let's say, semiconductor A, and I am denoting it with NIA. It would be square root of NCA into NVA into exponential of minus EGA over 2KT. Fine. Similarly, for NIB, it would be NCB NVB exponential of minus EGB over 2KT. Fine. So if I just divide these two equations, so what I will get, NIA over NIB, these things are equal, right? Because of this. So I can directly write that exponential minus EGA by 2KT over exponential minus EGB over 2KT. Fine. Then NIA and NIB, I can write exponential minus EGA minus EGB over 2KT. Fine. Then if I take log on both sides, then what will I get? Natural log of NIA over NIB is equal to minus EGA minus EGB over 2KT. So if I multiply this 2KT this side, so 2KT NIA over NIB, and here I will get EGB minus EGA. Fine. So all the quantities I know, this I know, this I know, KT I know, EGA I know, I need to find out EGB. Okay. So your EGB would be nothing but EGA plus 2KT multiplied by logarithm NIA over NIB. So what will it be? 1.12 plus 2 into what is KT? KT is my 0.026, right? By the way, what is the unit of KT? If I write this,
Electron volt.
and what is VT? KT by Q. What is the unit? What is the unit of this quantity? VT, thermal voltage.
Volts.
Right. So unit here is volts, and for this KT, the unit is electron volts. KT is energy, right? So natural log of what is my NIA? NIA is your 1.5 into 10 raised to 10 over 3.2 into 10 raised to 7. Fine. So if you calculate this, it will come out to be 1.44 electron volt. Okay. So this one is right. By the way, this is very close to your germanium, your gallium arsenide, right? It is very close to your gallium arsenide material. Okay. So you see, you note what are the point to note here, that if your EG is more, then your NI will be lesser, right? And why so? Because if at a certain temperature, if this is my EV and this is my EC, so if this gap is more, what do the electrons have to jump from this to this, right? For to get to become free electron. Those free electrons take part into conduction. These are valence electron. Valence electrons take part into conduction, but how? In forms of holes. Okay. The gap in the electron create a hole. That is a concept. Hole is not an physical particle. It is a concept. The absence of electron. Okay. So this free electron at certain temperature, it will get energized, this electron, and this will become free. So as you increase the gap, more energy will be required, right? So that's why as your for a particular temperature, if your EG is increased, then your NI will decrease. Okay, and the relation is very strong. It is exponential. See, this is minus of this. Okay, so I think you got the crux of this problem, and you can solve similar kind of problem if asked in the exam. Okay, so let's move on to the next problem. Okay, so it is mentioned that the probability of a state being filled, state means here we are talking about energy states. Okay, state being filled by an electron at energy, this is equal to the probability of a state being filled by a hole at energy this. So what is the probability of filling a state? It is given by your Fermi function, right? So this is actually probability of finding an electron at energy level E. Okay. So can anyone tell me what is the probability, what would be the probability of finding a hole at energy level E? Can you at least try to attempt?
1 minus 80. 1 minus 80.
And why do you say so?
Uh, Probability of hole plus probability of electron is equal to 1.
Yeah, you can say like that. Okay, just let me tell it in a better way. Yeah, you are right actually. So, see, if this is a, you remember your set theory concept. If this is an universal set, then if this is some probability of occupancy, then what is the remaining part is 1 minus 1 is your universal, right? Total probability. So, 1, so let me explain it in this way. Probability of finding is, let's say, small p. So what would be probability of absence is nothing but 1 minus p, right? Because there are no two other states. Either it is there or it is not there. So absence of electron means presence of holes. So whoever has answered has correctly pointed out that it would be this. Okay. So if you know this much, then the rest of the problem is very easy. So what they are telling? They are telling that probability of finding an electron at an energy level EC minus KT is equal to probability of finding a hole at energy level. What is that? EC minus 3KT. Okay. So how many of you have any difficulty understanding that this statement in the statement in the question is the same what I have written in this equation. Let's say this is equation A. Did you get it? How I write this question? This is probability of occupancy of hole at energy E equal to EC minus 3KT. Fine. Similarly, this is probability of electron occupancy at E equal to EC minus KT. And they have told us that these two should be equated. Okay. So the remaining part is pretty simple. So what you will do? You will just do this 1 plus. You know that what is your f of e? 1 by 1 plus exponential e minus ef by kt. Right? So in place of E, what is your energy level now? It is EC minus KT. So EC minus KT minus EF over KT. And it is inside the exponential, the power of exponential. Okay. So similarly, this would be 1 minus 1 over 1 plus exponential EC minus 3 KT minus EF over KT. Okay. So if I simplify this, 1 plus exponential EC minus KT minus EF over KT. So upon simplification, you can write it as 1 over 1 plus exponential EF minus EC minus 3 KT over KT. Okay. Because you see, 1 minus Fe would be nothing but your exponential E minus Ef by Kt over 1 plus exponential E minus Ef over Kt. So if you just divide it, then by exponential numerator and denominator, if you divide by exponential E minus Ef by Kt, you will get 1 plus, this will be 1 plus, and this will be exponential Ef minus E over Kt. Fine. So now what you can do, you can equate just simply. So these are same, these are same. So you can directly write that Ec minus Kt minus Ef will be equal to Ef minus Ec plus 3Kt. Fine. Then what would be your Ef? If you take 2Ef this side, this would be 2Ec minus 4Kt. Okay. So your Ef would be Ec minus 2Kt. So it will be B is your right option. 2Kt below the conduction bandage. Okay. So the main crux of this problem lies at this place. If you understood this, then it is very simple. Okay. So, okay, let's move on to the next problem. Not sure about the time. Okay. So, okay. So what is mentioned here? I may need one extra page. Okay. So what is mentioned there, that a silicon wafer is doped with 10 to the power 6 arsenic atoms. So what is the type of the silicon? Oh, what is the type of the semiconductor? When you dope it with arsenic atom, what should I write it? Na or Nd? Can anyone try to answer? When I dope silicon Nd, right? It is a donor type. The donor level Ed is located at. So this is your Ec. This is your Ev. So they are telling that this is my Ed and this value is 0.054 electron volt, right? So by the way, why do I show this Ed as a dashed line and Ec and Ev as a continuous line? Do anyone remember what we had discussed last week? Anyone can unmute and tell? Yeah, Sarthi, you can.
Sir, at ED, they are far from each other. L is greater, so that is discontinuous.
Yeah, basically, when you dope it like, what is your silicon atomic density? I told you that it is around your how much? It is around your 10 to the power 22. Let me just write the order, right? 10 to the power 22 per centimeter cube. This amount of silicon atoms are present, okay? And how do you dope? Your arsenic atom, maybe you are doping at 10 to the power 17 per centimeter cube, okay? So for how many silicon atoms there will be one arsenic atom? In 1 lakh of silicon atom, there will be one arsenic atom, okay? So the arsenic atoms are sitting far away from each other. So they do not actually create a continuous band, okay? So there we show them with a discrete symbols, okay? So anyway, this is just a recap, okay? So your Nd is given and your Ec minus Ed is told to be 0.054 electron volt, okay? So what percentage of the donor atoms are ionized at 77 Kelvin? By the way, do you have a feeling of this 77 Kelvin? Why these low temperatures are very important? What is the room temperature in Kelvin, by the way?
300.
Room temperature is your 300, right? And that is in degree Celsius, how much?
27 degrees.
27 degrees Celsius, okay? And this temperature is given as your 77 Kelvin, okay? So you can understand that it is your 300 minus 77 is 223, okay? 27 minus 223 is your, you see, minus 196 degrees Celsius, okay? So it is freezing cold, right? So these temperatures are called actually your cryogenic temperature, okay? There is a lot of research going on in cryogenic temperature range. You know that you if you have heard of that your quantum computing, have you guys heard of quantum computing? So you see, the IBM is making one kind of quantum computer. So those computers, they operate not on bits, but they operate on qubits. Okay, that is, just understand that it is similar to bit, but it has some kind of quantum entanglement, and it can allow multiple states to be present at the same time. Okay, so this cryogenic temperature analysis is very important. So why do we discuss about the 77K temperature cases? Because you see, for your for any computer for that sake to work in this world, you need to have semiconductors presence, or more precisely presence of silicon. Okay, so you need to observe how silicon behaves, or the transport in silicon behaves in those kind of temperatures. Okay, so these are called cryogenic temperatures. First thing should come into your mind, that your mobility will be a factor, right? Mobility will increase at low temperature. If you remember the mobility curve, you can see that the vibration of the atoms will be very less, and also your impurity ionization, from that point of view you can also see, right, that mobility will be comparatively higher than in room temperature. So there are various applications. Okay, another way point of view which this question demands is that you are asked to calculate what percentage of the donor atoms are ionized. Generally, what we do, we assume that Nd plus is almost equal to Nd generally, okay? But what is the assumption behind that? We are talking about room temperature, and we consider complete ionization, or complete or 100% ionization. But at low temperature, what happens that for ionization, how much energy is required? This energy is required, E ion. Electron should move from this place to conduction band. But even at low temperature, what is the temperature required? Kt, right? If your T is lesser, then your Kt will also be lesser. Then all the dopant atoms may not get ionized. Okay, so you will get lesser number of free electrons in your conduction band. Okay, so calculation of this kind, what I am going to show, is very important. Okay, so first thing, observe that at 77K, Nd plus will not be equal to Nd. Okay, and we are asked to find out what will be your Nd plus over Nd plus over Nd. Okay, this we are asked to find out. So what will you do? First thing is that the silicon wafer has to be charge neutral. Okay, so what is my charge neutrality equation? That is your Q into P minus N plus Nd plus minus Na minus should be equal to 0. Your net charge should be equal to 0, or other way to say that your net positive charge should be equal to net negative charge. So you see that your what about your P? P is nothing but your Ni square over N, right? Minus N plus Nd plus, and this acceptor ion is, no acceptor ion is present. So now my question is, can I ignore this quantity also? Can anyone like to comment? Should I ignore this quantity? You remember, right? The plot carrier concentration I have shown you that this kind of trend it takes, right? This is your Ni and this is your ionized, right? So what is the temperature I told you for silicon at this range? This is around 300 K. And what is this temperature? This temperature is around 50 to 100 K. So you see that around your 77 K, let's say this is your 77 K, your Ni is very less, right? Obviously it has to be, because your Ni is what? Root over NC e to the power minus Eg over 2kT, right? So if your T is large, this quantity is small. Sorry, T is small, this quantity is large, and e to the power minus that quantity large means this Ni is almost, you can neglect as 0, or it will be very small. So what you get from there, that this you can ignore. So you will get N equals to your Nd plus. Fine. And this is also true from this plot, that in this range I have told you that in this range N would be equal to Nd plus, at this range it will be Nd, and at this range it will be N equal to Ni, right? This is called your intrinsic region. This is called your, what are these two regions called, by the way? Anyone?
The center region is extrinsic region,
Right. And what is the left
and the
one called?
leftmost region is freeze out.
Right. So in which region we are right now? We are near the freeze out region, right? Where my N will be very, very small. Fine. So your N is this Nd plus. Okay. So now how do you compute? If you have gone through the lecture, you will come across this formula, right? This your Nd plus would be equal to Nd over 1 plus Gd into exponential Ef minus Ed over Kt. Have you seen this formula? Anyone?
Yes, sir.
Okay. So this is called your degeneracy factor. Okay. Ef you know, Fermi level. Ed you know. What is Ed? Ed is nothing but this Ed. Okay. Just bear with me that I am using the small and capital subscripts. These are same. Okay. So how can I solve this? This N equal to Nd plus is equal to Nd over 1 plus Gd multiplied by exponential. What I can write this as Ef minus Ec plus Ec minus Ed over Kt. And why do I do so? Because I know this value, right? This value is known to me. And this part, you see, if you note what is your N equals to Nc exponential minus Ec minus Ef over Kt, right? So that is nothing but NC exponential EF minus EC over KT. So I can write this as this over 1 plus GD, and this part I can write as N over NC, and this part I can write as e to the power EC minus ED over KT. Okay, and this is your N. So now what we have, N equals to ND over 1 plus, now this I know, and this also I know, because KT I know. What is KT? KT is equal to 1.38 into 10 to the power minus 23 into your T is 77. Okay, this joules. Okay, or in electron volt, if you want to calculate, 0.026 into 76 over 300. Okay, so if you calculate this 0.026 into 76 over 300, you will find out it will be 6.6 millivolt, milli electron volt. Okay, at 77K. At 77K, KT is not 26 milli electron volt. Okay, so what I will do, I will combine, I will write this N and I will combine it to be some quantity, let's say 1 over tau. So what is my tau? Tau is nothing but NC over GD exponential minus EC minus ED over KT. Okay. So now what do I have? I have, if I just multiply this into this, 1 N plus N square by tau equals to ND, or tau N plus N square equals to tau ND. So N square plus tau N minus tau ND equal to 0. So this is a quadratic equation. This I can solve as N equals to minus tau plus minus root over tau square plus 4 tau into ND over 2. That would be minus tau over 2 plus minus root over tau by 2 whole square plus tau into ND. Right? So this is a positive quantity. So obviously that my N will have to take this solution, because carrier concentration cannot be negative. So this will be tau over 2 plus this plus tau ND square root. Okay. So now what are the things you need to find out? You know NC, you know GD. Are these given in the question? Yes. This is your GD. GD is given as 2. Your NC is given as 4.2 into 10 to the power 18. Okay. So GD is given, NC is given. This quantity is given as 54 milli electron volt. KT you have found out to be 6.6 milli electron volt. So you can obviously calculate tau, right? So what will your tau be? Tau will be your around, if you calculate 6.4 multiplied by 10 raised to 14. Okay. So now if you put this quantity into this equation, or 6.4 into 10 raised to 14 over 2 plus 6.4 into 10 raised to 14 by 2 whole square plus what is your tau? Tau is your 6.4 into 10 raised to 14. And what is your ND? ND was your 10 raised to 16, right? ND was your 10 raised to 16. So 10 raised to 16. So if you compute this quantity, you will find out your N to be 2.23 into 10 to the power 15 centimeter cube. Okay. So this N is nothing but your ND plus. Okay. So what is your percentage ionization? Is your ND plus over ND? That is your 2.23 into 10 to the power 15 over 10 to the power 16, right? That you will find out to be that you will find out that 2.23 into zero point 0.1. So and percentage ionization need a 100 multiplication. So you will find out this to be 22.3%. Okay. So your answer would be C. So you see the difference. When we go from 300 Kelvin to 77K, the percentage ionization almost changed from 100% to 22.3%, right? So earlier we seen that 100% ionization is there at 3 equal to 300K. Now we are seeing that T equals to 77K, we have percentage ionization of 22.3%. Okay. So do you see that if your percentage ionization is reduced, then what happens? Then your ion impurity, ion scattering will also reduce, right? So this is how this problem will be solved. So this is I would say one of the most difficult problems you will find in this course, in this chapter of this carrier concentration and your statistical mechanics. So please go through this problem again if you did not understood anything, if you did not understand anything. Go through step by step derivation, make cases yourselves. Suppose you may take some arsenic atoms, some boron atoms, then combine and then check, make cases and solve it by yourself. Okay. So this is how this problem is solved. So if you have any question in this regard. Okay. If not, so let's move on to the next problem. Let me add another page. Okay. So the last problem from assignment this last week 3. Okay. What was intended? For a certain semiconductor, the density of states. Okay. I want to interact with you guys. This problem I want you to help me to solve. Okay. You know all the steps. You just help me to solve. Whenever you will get stuck, I will cover it up. Okay. So Srihari, can you try to help me?
Yes, sir.
Okay. So keep yourself unmuted. Okay. For next 5 minutes. So let's solve this problem together. So for a certain semiconductor, the density of states of a conduction band is this and valence band is this. Okay. So your GC of E is given as A of E minus EC. Fine. And GV of E is given as B of EV minus E. So what is the first observation? First observation is that it is not the conventional one, the square root. We assume the parabolic one, right? You see, we always assume that if this is my GE and this is my E axis and it is my EC, conventionally we assume this, right? And from that we derive the formulas. Now what is given? They have given that it is like this straight line. Now do the calculation. Okay. So Okay, so this is given where A and B are two non-zero constants. Okay, these are constants. Assume Boltzmann's distribution for the type of carrier. By the way, what is Boltzmann's distribution? What is Fermi-Dirac distribution? Fermi-Dirac distribution is this. Okay, 1 over 1 plus exponential E minus EF by KT. Right? This is your Fermi-Dirac. What is your Boltzmann's distribution or Boltzmann's Maxwell distribution? Boltzmann's Maxwell distribution. It is proportional to your, it is not proper. Let me just write in with a constant. Exponential minus E over KT. Okay. So, do you know any other kinds of distributions? Anyone? Okay, give me an example of this Fermi-Dirac distribution. Which give me name of a particle which follows this distribution.
Electron.
Electron. Okay. More generally, they are called fermions. Okay. So what about someone? Okay. So what about this Boltzmann-Maxwell distribution? Give me an example that tell me a name of a particle or some molecule which follow this kind of distribution. Just attempt, try. The gas molecules. Okay. If you keep gas molecules in a jar, the way they distribute the energies among themselves or they occupy the energy states among themselves is being followed by this Boltzmann-Maxwell distribution. They are also called Boltzmann's gas. Okay, these are the general terms. And electron is one example of a fermion. Gas molecules or these natural gas molecules are one example of a Boltzmann gas. Okay, sometimes you will see that electrons are also considered as a Boltzmann gas. And can you tell me why that's so? You see, when your E minus EF will be greater than 3 kT or around greater than 3 kT, then this quantity will dominate, right? Then this one will get neglected and this will go up and it will behave like this kind of distribution, okay? Exponential minus energy of this, fine? So that's how your Fermi, for certain condition, we take Boltzmann's approximation, okay? And another, to complete the set, there is Bose-Einstein's distribution also. This is your Bose-Einstein distribution. Let's say it behaves something like that, okay? And the example is that what kind of particles these are? These are called bosons. So example would be your photon or light particles, okay? This can have fractional spins. Those are some different concepts, okay? Let's not go into that. Just to make you sure that you know this much, if somebody asks you that how many kind of distributions of energy are there for any tiny molecules or tiny particles, you can say that there are three types, okay? This is classical and these two are quantum mechanical in nature, okay? Okay, so let's go back to our problem. So it is mentioned that is the energy conduction band is compute the intrinsic Fermi energy. Okay. So what is intrinsic material? What is the basic definition of intrinsic material, by the way? So I was with whom?
जो
Shri.
डोप नहीं होते.
No. What is the definition? How can you tell them that these are intrinsic?
They are not doped.
Right. But from that we can infer that. By the way, why do we do doping?
To make them more
Conductive, right? To
more
make them more conductive, we need to have some kind of carrier flow in them. So we try to increase the number of carriers. Okay. So what are the kind of doping you have? N type or P type? For a N type, number of electrons are more than holes. For P type, the number of holes are more than electrons. So what is intrinsic? Tanish?
Concentration of electrons is equal to concentration of holes.
Exactly. So the concentration of electrons is equal to concentration of holes. Okay. That is the basic definition. So now I need to find out these two quantity because I was asked to find out intrinsic Fermi energy. Okay. Fine. So how can I compute? Let's say, let me compute N. So how can I compute N if I know G and F? I was with Srihari. Srihari, please unmute and assist me.
In terms of density of states,
Right. So what do? We do this kind of integration, right? If you remember that how we come out to be. This is your Fermi-Dirac distribution or whatever distribution here it is Boltzman. Let's say this is your distribution. This is your density of state. We multiply them and then take the area from EC to, and we assume that the conduction band is lying till infinity. Okay. So we integrate and compute the area under this. Fine. That is the way how you get your formula, that NC of exponential minus EC minus EF by KT, right?
yes.
So this is the same thing. So this problem is designed to make you understand the process, how you calculate N and P. Okay. So what do I have? I know everything to compute this integration. EC I know. GC I know. What is GC? A of E minus EC. F of E I know. It is exponential E minus EF by KT minus E. Sorry, I missed this. Right. Okay. E minus EF by KT, and you have this DE here. So can I make it in a convenient form? If it is EC, it is infinity A of E minus EC exponential minus E minus EC plus EC minus EF by KT into DE. Fine. So these are my constant terms, EC minus EF over KT. So these are my constant terms, and your integration is from this to this, E minus EC a to the power minus E minus EC over KT into DE. So let E minus EC over KT is equal to X. So your DE would be equal to KT into DX. So this is nothing but change of variable. So I can simply write A to the power minus EC minus EF over KT integration this limit will become 0 to infinity from this, and I will have E minus EC will be x into KT, and e to the power minus this will be e to the power minus x, and dE would be KT into dx. So I will have a KT square out e to the power minus EC minus EF by KT. So now tell me, have you seen this kind of integration anywhere else? Tanish, what is this function?
We have seen it in starting this
In your
exponential
no,
function.
in your engineering mathematics, you must have seen this, right?
Okay.
Gamma function, remember?
Yes, sir.
Right? This is nothing but your gamma 2. Okay. Remember your gamma
Yeah.
of let's say a would be equal to 0 to infinity x to the power a minus 1 e to the power minus x dx. So what is gamma 2 value? Gamma a is nothing but a minus 1 factorial, right? Do you remember this, guys? So this will be nothing but your 1. Okay, this definite integral is nothing but your 1. You remember in your engineering mathematics 1 or 2, you must have studied that this kind of special definite integrations, beta function, gamma function. So what you can do, if you do not remember it, just go today after the session to Wikipedia and search gamma distribution. Okay, gamma distribution, and read the article. You may not understand everything, but read the article. You will gamma distribution and then search gamma function. You will get to know that how gamma functions come about. Then you will not forget it. Okay, this is you take it as a home task. So moral of the story, your this function will be, integration will be this kt square into e to the power minus ec minus ef over kt. Fine. So this is your n. So n is your a kt square exponential minus ec minus ef over kt. Fine. Similarly, you can write for p also. It was b, and same integration steps you can follow. And what will this be? It will be your ef minus ev, right? If you do the integration properly, you will see that this will come. So now what is my intrinsic criteria? That n has to be equal to p. That means your a kt square exponential minus ec minus ef over kt has to be equal to b kt square exponential minus ef minus ev over kt. Fine. We need to find out what? We need to find out ef, the intrinsic Fermi level, which we also call ei. Okay. So this will get cancelled, and it is also mentioned that a is equal to 2b. So this, there will be 2. If it is 2b, then bb will also get cancelled, and if I take exponential to that side, it will be minus ef minus ev minus ec plus ef over kt. So what will I have? I will have kt ln2 is equal to minus 2EF minus EC plus EB. That means minus KT ln2 will be 2EF minus EC minus EB plus EB. So you will have your 2EF is equal to EC plus EB by 2 minus KT ln2 and okay, this 2 will not be there if I divide it by 2. So it will be half. Fine. So if you compute, and also some other information is given that assume EV equal to 0. So your this term will also be 0. So you will see that EC by 2 minus half into 0.026 into ln2. Okay. So you will find out your EF to be EC by 2 minus this will be your 9 milli electron volt. Okay, if you do milli electron volt, then I would say you take this as milli electron volt, 6 milli electron volt. Okay, so this will be your answer. So A will be your answer. Okay. So any question till this point? So what is the crux of this problem? You need to understand this. Okay, how do you calculate the carrier concentration? Then you need to understand this. What do you mean by intrinsic? The rest are just simple mathematics. It may not look simple at the beginning because gamma functions are involved, but believe it, take my words that there are much more difficult integrations. If you would not take Boltzmann's approximation here, you would go to your Fermi integration. Okay, that and those Fermi integrals are very terrifying. So for your course, you don't try to attempt to solve this with Fermi distribution. You go with Boltzmann approximation of Fermi integration or Boltzmann distribution. Okay. So let's move on. Okay. So today's main content starts here. Okay. The fourth days. 3 scattering mechanisms are present in a particular semiconductor material. Okay. 3 scattering mechanisms are present. So just for refreshment, just for refreshing your memory, I have told you in last session that what kind of scattering mechanisms are there, possible scattering mechanisms. Name a few. Shiveri, you name one.
Photon scattering.
Phonon scattering, right?
Yes, sir.
Okay. Tanish, you name one other than phonon scattering. Okay. Anyone else want to?
याद नहीं आ रहा सर मेरे को.
Im- impurity scattering.
Impurity scattering or Coulomb scattering, right? And anything else? So they have told that 3, right? We know that these 2 are major, but I have told you 5, 6 more kind of scatterings. Okay. So there would be surface scattering, there will be defect scattering, there will be interstitial space atom scattering. Okay. Many mechanisms are there. Okay. So we are told that there will be 3 scattering. Okay. So you may think that you might think that we know only of 2 scattering. So how can there be 3 scattering? Okay. So this is the reason that there are more than 2 scatterings, but we generally talk about 2 main scatterings. So they are told that your mu1 is given as 2000 centimeter square per volt second. mu2 is given as 1500 centimeter square per volt second. If only one scattering is present, then what would be my mobility? Okay, and then it is given that 500 centimeter square plus volt second, and they are asking us what is the net mobility. So what law do we use to find this out? We use Matthiessen's rule, right? Anyone heard of this? So this is the Matthiessen's rule. So similarly, if other types of scattering are present, so it will just go on like this. Okay. So this is Matthiessen's rule. Okay. So you simply plug in your values in this formula, that your 1 over 2000 plus 1 over 1500 plus 1 over 500, and you will get your mu to be around 315.7 centimeter square per volt second. Okay. So this would be your answer A. So now tell me, now let me give you some more insights. Okay. And believe me, this may come in exam. What is mu? What is the formula of mu in terms of effective mass and relaxation mean free time?
Q into T collision by M star.
Q and M are constant, right? M star are constant, can be taken care as constant. So Mathiessen's rule, this is also Mathiessen's rule. Okay. 1 over tau is equal to 1 over tau 1 plus 1 over tau 2 plus 1 over tau 3. Okay. So if this is given, then also you can calculate the net free time between collisions. Okay. So this is also Mathiessen's rule, or this is the main form, the actual form of Mathiessen's rule. These all are derived forms. Okay. Similarly, if I tell you in terms of sigma, can I write this one? Conductivity. Can anyone comment? Sigma is what? Your Q mu into N, right? So your N and Q if constant, then Matthiessen rule applied to this also. Are you getting it? How this is coming? 1 over sigma 1 plus 1 over sigma 2 plus 1 over sigma 3. So what will this be? 1 over Qn into mu 1 plus 1 over Qn into mu 2 plus 1 over Qn into mu 3. So 1 over Qn, if I take common, you will take mu 1 plus 1 over mu 2 plus 1 over mu 3. And this is nothing but your 1 over mu, right? So it will be 1 over Qn mu. That is 1 over sigma net. Fine. So this is also Mathiessen's rule. So instead of in this question, if instead of mobility you are given conductivity, then also you can write, solve this problem. If you are given mean free time, then also you can solve this problem. Fine. And what is the third form? Rho is rho 1 plus rho 2 plus rho 3. This is rho is resistivity. Why so? Because simply because rho is nothing but 1 over sigma, right? So again, if three materials are given and you are told that scattering is there, so don't think that how, if scattering is given, how I can compute that resistivity. The logic is that resistance in a material comes from the random thermal motion of the electrons in the material, and that random thermal motion is due to the scattering, various scattering mechanisms. So if you know various scattering mechanisms, either your mobility or your resistivity individually, you can calculate the net resistivity. So anyone have any question regarding this? Okay. So these three formula also you remember. It is not only this. So these four are the same formula. Okay. This 1, 2, 3 and 4. This all four are can be solved using Matthiessen's rule. Okay. So let's move on to problem number 2. Consider a semiconductor in thermal equilibrium. Assume that the donor concentration varies. So first tell me what is thermal equilibrium? What is your concept about thermal equilibrium? Anyone?
It is at room temperature.
No, not necessarily. See, thermal equilibrium has to follow certain conditions. First one, no net transfer of energy. Okay. Every action or every process has equal reversible process. Okay. Third condition is that no external excitation. External excitation. What is excitation? Source of energy. Okay. That we call excitation. No external excitation except constant temperature. It may not be room temperature, but a constant temperature. The temperature gradient should not present. The temperature must not vary. A constant temperature. And what is the fourth condition? Principle of detailed balance. Principle of detailed balance. What does principle of detailed balance means? Suppose if a process is composed of many sub processes, so every sub process has to have also some reversible process, equal reversible sub process. Okay. So given these conditions, let me ask you one thing. If you can see a semiconductor slab, if you can see silicon, is that in thermal equilibrium? Anyone? It's a very interesting question. Would you like to attempt it? There is no fun if I tell you the answer, okay? At least you should try to attempt it. If you can, suppose this is a semiconductor slab. If I am able to see it, if you are able to see it, is it in equilibrium?
There is no thermal equilibrium
Why?
because there is presence of light.
There is presence of light. Exactly. Excellent. That light is a source of energy. And what we have told that except thermal energy, there should not be any presence of any other form of energy. Thermal energy also some constant temperature, okay? Because I am able to see the semiconductor or silicon slab, that means there is some reflectance. That's why I am seeing it. That means there is presence of light. That means it is not in equilibrium. Okay, excellent answer. So, okay, and obviously if there is no net flow of energy, there will be no net current, right? So that is what mentioned in the question. Consider a semiconductor in thermal equilibrium. That means no current. Assume that the donor concentration is like this over a range of this. N0 is constant. Assume 3. What is the value of electric field? Okay. So what is my J? This is NDX. That means I can assume that it is an N-type semiconductor. Okay. N-type semiconductor. So the electron current must be zero at thermal equilibrium. Similarly, the minority carrier current, hole current will also have to be zero individually. Okay. And what are the components of current? What are the sources of current, mechanisms of current? In this course, you will only be focusing on two types of mechanism. One is drift, another one is diffusion. So what is drift? Presence of potential gradient. That means if there is some potential gradient, so this is V1 and this is V2, that means there is some presence of electric field. So if there is electric field, carriers will move, charged carrier will move. We have discussed this in last two sessions. So this mechanism is called drift current. Okay, drift current due to electric field. Or what is electric field? Is nothing but your minus d phi dx potential gradient. Fine. What is the other form of current in our course? Is that diffusion. What is diffusion? Suppose you have too many carriers here, okay, and this is some kind of very small number of carriers present, and you connect this with a pipe. You think what will happen? Carriers will flow from high concentration to low concentration area, right? That means if the concentration is N1, if it is N2 and it is also having a gradient, or dN of dx or dP of dx is not equal to 0, or there is a gradient, that means there will be diffusion. From higher concentration, they will go to lower concentration, right? When you light up your you see your let's say some kind of smoky kind of thing, okay, let's say you light up an agarbatti, then there will be smoke coming out of, and there will be high concentration, and it will eventually get distributed and float around the entire room. That is what is called diffusion, the process of diffusion. So can anyone tell me if carriers can move from low concentration to higher concentration also? These are from your 7th and 8th standard science. Okay. We know that.
Without energy, we cannot answer.
Are you sure? What
You have
about
to apply some
osmosis?
pressure. Osmosis is movement of the solvent from the higher concentration to lower
Right.
concentration to the higher concentration.
Exactly. The same thing, right? Lower
When we apply
concentration
a
to.
pressure related to osmotic pressure, we can conclude it is a reverse osmosis.
Exactly. That is what is used in your filters, right? RO. So
Yes.
movement of lower to higher concentration is also possible, but that process is completely different. Okay. So remember that diffusion is from higher concentration to lower concentration. So we will only concentrate about these two kind of mechanism. So if charged particles are higher concentration move to lower concentration, obviously there is a movement of charge. Obviously there will be movement of current. For that there will be current also, right? So current generates due to two mechanisms, drift and diffusion. In our course there are other mechanisms also. Due to thermal gradient also in semiconductors you can get currents. Okay, anyway, so what happens that your Jn is equal to 0. So Jn drift plus Jn diffusion is equal to 0. Drift current is given by Q mu n electric field, and your diffusion current is given by Q dn of dx. Okay, what is dn? It is nothing but a constant, which diffusion constant you may say. It is similar to, you say, your mobility, and these two are related by your Einstein's relation, right? Kt over q. This relation is valid under Boltzmann approximation only. Okay, Boltzmann's approximation or Boltzmann's distribution only. Remember that it is not valid if we take the Fermi-Dirac distribution to calculate n and p. So this part we know that this equation. Now it is told that assume that the donor concentration varies as this. Okay, where n0 is a constant, assume what is the value of electric field. Fine. So q and q gets cancelled. So what do I have? Mu n into E of x is equal to minus dn over x. Okay, so I can assume my n equals to nd of x. So dn of dx would be dnd of dx, that is equal to minus 10 n naught e to the power minus 10x. So in one hand I have mu n. What is my n? N is n0 e to the power minus 10x into E of x is equal to minus dn into, and what is that? Minus 10 into n0 e to the power minus 10x. n0 minus e to the power 10x I can cancel, and so mu n into electric field is equal to dn into 10. So what is E of x? E of x equal to d of n by mu of n into 10. What is d of n by mu of n? I told you that it is kt over q, right? And at 300, what is kt over q? 0.026. 0.026. What is the unit will be kt over q? What is the unit? Sri Hari has told at the first question, right? At the first slide I have asked this question. It will be volt. So volt into, this is your, it will be your 10. Okay, so let me just remove this. So your answer would be 0.26 volt per meter. Okay, because all we have done in SI unit. Fine. Is this okay, or you need some detailed discussion on this? Okay, I think it was pretty straightforward. Once you read the lectures or once you have gone through the lectures, you will find out that it is pretty simple. Okay, but these two mechanisms, please read this thoroughly from the lectures. Okay. Okay, so okay, let's move on to problem number 3. Some kind of profile is given. Okay, this is some kind of profile, which is x, and let's say this is some concentration profile. Okay, here electron concentration varies linearly as shown in the above figure. Concentration of electron at x equal to 0 is n and x equal to L is 0. Calculate the total number of electrons present in the material given the cross section is this. Okay, so let's say this is your material. Okay, fine. Let us assume that this cross section is A. Okay, and we are only the concentration is varying only in this direction, x direction. Let's say this is y and this is your z direction. Okay, so concentration gradient only varies in x direction. Okay, so whatever we will find in x direction, we will just simply multiply it with A and we will get the total answer. So similarly, if it is a, let's say it is a circle. Okay, let me draw, it is a circle and the radius is r. So what is the area? Area is pi r square, right? So now if you make a cylinder out of it, so what will be the volume of the cylinder? If this is
Area into
H,
height.
right, this is this into H. Okay, the same concept is applying here. Just for visualization sake, I am explaining this part. Okay, and this way it is mentioned that it is like this straight line behavior. The carrier concentration is like that. Means here you will have high number of electron and the electron concentration is gradually decreasing. Okay, so this is given. Now they are asked that concentration this. Okay, so what is the first thing? This unit is centimeter cube, centimeter to the power -3. Okay, so we need to find out this area. If I find out this area, I will get number of electrons in this sheet, or I would say if I make it A, B, C, D, number of electrons in this I can get if I just integrate this straight line from this to this, or I simply take that area of the triangle. Okay, so number of electrons present in x direction would be what? Half into height is what? N into L, right? Half NL, right? And now I need to just extend it into this direction. Okay, so and what, by the way, what is this unit? This will be centimeter square. Okay, this is centimeter cube, this is centimeter, so it will be centimeter to the power -2. So total number of electrons would be half NL into area, that is your half ANL. Okay, so this will be your right answer. And what is the other way to do it? If it is not a straight line, then you cannot just take the area of the triangle simply. So you need the equation of that curve. Okay, so for a straight line, you know how to find the equation. If 2 points are given, how to find out the equation? Y2 minus y over x2 minus x is equal to y2 minus y1 over x2 minus x1, right? If a straight line is passing through 2 points, this is your x1 y1, let's say, and x2 y2, 2 points it is passing through, then this will be the equation. Then you simply make y as a function of x and then you integrate it from 0 to L. Fine, that way you can get the area under the curve and it will give you the same value. And for any other curve, this form you need to know, y of fx, this form you need to know, and then you simply integrate to get the area under that that curve. So you will get in one direction, and then you vary it in the, if multiply it with the area, and if even if the in other two direction it is also varying, then you have to make a volume integration, right? You have to integrate it in 3 dimensions. Fine, x you can take out separately, y component you can take out separately, and z component take out you separately. Okay, that you can do. Okay, so it was pretty easy. Let's move on to next problem. Okay, so it is mentioned that a semiconductor has following properties. Okay, dn is given, dn is given, dp is given, tau n is given, tau p is given. Fine. The semiconductor is p-type with this and held in equilibrium at this. Source is turned on to produce excess carriers at the rate of this. So by the way, first tell me, have you read about this chapter, excess carriers and all, continuity equation and all? Have you gone through? Or let me just write this equation. Just tell me that whether you have rate this kind of stuff. Otherwise, I will skip it today and explain next week. Okay, this plus Gn minus delta n by tau. This is your rate of change of electron, rate of change of current with respect to space. This is your generation. This is your recombination. This equation is called continuity equation. Continuity equation for electrons. So have you read this thing? Anyone?
Yes, sir.
You have read
Yes, sir.
this? Okay.
Yes,
Do
sir.
you
Sir
know
had
how?
taught.
Okay, sir has taught, right? So do you know how this come about?
Yes, sir.
You take a cube, you take a cross
J,
section,
J in, yes, sir. J in is equal to J out.
J in equal to J out.
J
Okay,
is equal
okay.
to output.
Exactly.
Flow,
So
flow.
flow. Right, right. So okay, then I will discuss this problem. Fine. Okay. So by the way, to start solving the before starting start solving the problem, I just want to mention one thing and note this thing very carefully if you want to do any kind of future courses on these electronic devices. Okay, note this thing very carefully. There are 5 golden equations in semiconductor devices and circuits. Okay, 5 golden equations. If you know this and whatever you have read till now, you can understand everything. Okay, so what are these? Continuity equation of electron, continuity equation of holes, current equation of electron, current equation of holes, and Gauss's law. Okay, these are the 5 equations. So continuity equation of electrons is, it goes something like this: djn over dx plus gn dash minus dn by tau n, ddp over d tau minus djp over dx plus gp dash minus dp over tau n. This is dp is p subscript. Okay, this is excess holes, dn is excess electrons. How do you have excess electrons and holes? By some other mechanism. You
Through doping.
until through doping, you will not have excess holes and electrons. You need to add some other sources, right? You may say that you need to shine some light, or you may need to put some bias to create excess electrons and holes. Okay, these are the excess part whatever you have in your equilibrium. Okay, doping is a phenomena which can happen at equilibrium also, right? I can have a p-type semiconductor and it can be at equilibrium. Okay, so these dp and dn are not due to the doping, but on top of doping due to some other mechanism. Either you shine light on top of it, or you apply some bias, or you keep some thermal gradient. Okay, so you disturb the equilibrium. Okay, the concept of Fermi level or the equilibrium concept will not be valid then. It will have your quasi Fermi level concept. Okay, those we will discuss later. So, and this is your total current equation. This we have also seen. Q mu n into epsilon electric field plus Q dn into dn over dx. Similarly, Jp Q mu p electric field plus Q dp. This should be minus, and I assume that you know why it would be minus. And what is your Gauss law, by the way? Gauss law is this, right? Del E upon del x is equal to rho of epsilon, where rho is charge density. And what is rho? Rho is equal to Q, same thing, Q equal to into P plus ND plus minus N minus NA minus. Okay. And also your potential equation, you know, that minus d phi by dx. Okay. So from Gauss law also you can derive that d dx of minus d phi by dx equal to your rho over epsilon. That means your d square phi by dx square equals to minus rho over epsilon. This is also known as Poisson equation. Okay. So these are the equations you need to understand very carefully. Actually, this is the crux of this entire course. Okay. To make you understand this 5 set of equations and these auxiliary equations. If you understand this much very carefully, believe me, all the PN junction, MOS capacitors, whatever else is there in the remaining course, you will find it very easy. Okay. So make sure you spend enough time to understand each and every integrity of this these equations. Okay. So okay. So now what is the question? Question is that okay. So semiconductor is P type with Na. Okay. Semiconductor is P type. It is mentioned, right? So let us take with the letter, and what is the excess electron concentration? Okay, good question. So Srihari, for you this you mentioned that it was, I assume that you have some difficulty in the concept of visualizing this delta P and delta N. Okay, so this is a P type semiconductor. Fine. It is mentioned that okay. Just let me remove this. Read the question very carefully. It is mentioned that a p-type semiconductor is held in equilibrium for t equal to t minus 0. Fine. So t equal to 0 microsecond. Before that, we have equilibrium. Now, Srihari, tell me at equilibrium, what will be the carrier concentration of p-type? Will holes be more than electrons?
Yes, sir.
Right? Holes will be more than electrons, right? But again, it will be in equilibrium. That means those excess carriers, what we are talking about, is not due to the doping. First point. Second point is that at t equal to 0, an external source is turned on, which produces excess carriers at this. That means at t equal to 0, some source is turned on, which is producing excess carriers. Okay. excess carriers. Depending upon what kind of source it is, there may be electrons, holes, and electron hole pair will also be there. Suppose it is a light source. Light will fall upon the semiconductor and it will create an electron hole pair. That means delta P will also increase and your delta N will also increase. Fine. These are called excess carriers. That means your now N would be your N0 plus your delta N, and your P would be P0 plus delta P. Fine. This suffix 0 denotes the equilibrium condition. Okay. And they are told that at t equal to 2 microsecond, this is again off. Okay. Source is off. External source is off. In this case, source was on to generate some excess carriers. Okay. So now they want us to find out what is the excess carrier concentration excess electron concentration at t equal to 2 microsecond. Okay. So what will we do? We will consider equation 1 of our 5 golden equations. Continuity equation of electron. So what is that? This is dt 1 over q. Okay, I did not mention 1 over q here. Okay, it will be 1 over q djn over dx plus gn dash minus delta n over tau n. Okay, this equation, continuity equation for electron, we know. Fine. Now what will you do? We simply write it like this: 1 over q d dx. What is jn? What is jn? I can write this from this equation 3, right? But so what was my jn? Q mu n n e plus q dn this plus gn dash minus delta n over tau n. Fine. This jn I have replaced here. Okay. Now what will you do? We see that the external source is not some kind of electric field. Okay. It is not mentioned. So my this quantity is 0. And we assume that uniform generation of excess carriers. What does that mean? That means that suppose light is shined upon this semiconductor, the amount of electron hole pair generated here will be exactly same at here throughout this x direction. Okay. So if it is a constant line, this d, if it is a d n or dp is a constant line, then its slope will be 0 with respect to x, right? So this will also be 0. So now what do we have? We have d dt of excess carrier concentration equal to gn dash minus dn over tau n. Fine.
Sir, sir,
Yeah. Yes,
since we
please.
have given p-type semiconductor, why can't we consider p equal to p naught plus del p?
No, we are required to find out this, right? We are required to find out electron concentration,
Okay, sir.
right? So that's why we are using the continuity equation for electrons, right? The equation is valid even if it is p-type, n-type, or even if it is compound semiconductor, or compound means your compensated semiconductor also, right? P and N both are present. Then also it will, these equations will be valid. Okay.
Okay.
So now what I have, now this is a first order differential equation. How do we solve this equation? Let's go step by step. So we have dn over dt equal to gn dash minus, just let me do this, gn dash tau n minus delta n over tau n. Okay. So d of dn over gn dash tau n minus dn equal to dt of tau n. Fine. So what we have, if we integrate it, okay, what will I have? I will have minus of log gn dash tau n minus delta n equals to, this tau n is constant, so it will be t over tau n. Fine. Plus some constant, let's say, because I am doing it indefinite integration. Okay. So now at t equal to 0, what was my dn? dn was 0, right? No excess carrier because there was no source present. Fine. So c equal to what? If t equal to 0, then c equal to this quantity will get, this quantity will get 0. So I will have minus ln gn dash into tau n. Fine. So I can write, minus ln gn dash tau n minus delta n equals to t over tau n minus ln gn dash into tau n, right? So if I take this at this side, so what will I have? I will have ln, let me just change the signs here, it will be easier to compute. So ln gn dash tau n minus delta n minus ln gn dash tau n would be equal to minus t over tau n. Just let me add a page. So I will have ln gn dash tau n minus delta n over gn dash tau n equals to minus t over tau n. So if I just do this, gn dash tau n minus delta n, right, is equal to gn dash tau n into exponential of minus t over tau n. Log is coming at this side. So you see, we need to find out delta n, right? Delta n would be nothing but gn dash tau n minus gn dash tau n of e to the power minus t by tau n. So your dn of x should be, sorry, the variable is t, is equal to gn dash tau n 1 minus e to the power minus t over tau n. Okay. Now they are asked that all the values we know, gn dash is given, tau n is given, t is 2 microsecond is given. So what is tau n? Tau n is given as 1 microsecond. Okay. Tau n is given as 1 microsecond. and Gn dash is given as 10 raised to 20 centimeter cube per second. Okay, so Dn 2 microsecond is equal to 10 raised to 20 into 1 into 10 raised to minus 6, 1 minus e raised to minus 2. So if you compute this, your value will come out to be around 8.65 into 10 raised to 13 centimeter cube. Okay. So this would be your right answer. Okay. So these are the steps. So you see, if you have gone through the lectures properly and clear your concept, these all are just now mathematics. Okay. So please, I am requesting you to make sure you understand these sets of equations very clearly, and also with all kinds of plots. You plot everything. Okay. Then you will have a better feeling about what is going on and what is not. Okay. So this is how you calculate the excess carrier concentrations. So let's move on to the next problem. A sample of semiconductor has a cross-sectional area of this. Okay. Let me just draw this. Okay. And a thickness of 0.1 centimeter, and a cross-sectional area, this surface area is your 1 centimeter square. Fine. Determine the number of electron hole pairs that are generated per unit volume per unit time by the uniform absorption of 1 watt of light at a wavelength of this. Assume that each photon creates 1 electron hole pair. Okay. That means light is getting shined on this and electron hole pairs are getting generated. Okay. One photon is creating 1 electron hole pair. So first we need to find out how many photons are there in 1 watt. Okay. How do we do that? What is the energy of a photon? 1 unit of photon? Anyone? Energy of photon equal to h nu, right? What is nu? Hc by lambda, right? What is the velocity of photon?
3 into 10 power 8
It
meter per second.
What is the value of h? Joule second. Okay. Multiplied by 3 into 10 to the power 8 meter second inverse. Okay. Divide by lambda. What is lambda? 6300 angstrom. So 6300 into 10 to the power minus 10 meter. Okay. Meter cancel. Second inverse second cancel. So I will get, if I calculate this, 6.626 into 10 raised to minus 34 into 3 into 10 raised to 8 divide by 6300 divide by 10 raised to minus 10. So I will have 3.155 into 10 raised to minus 19 joules of energy. Fine. 1 watt is how much? 1 joules per second. 1 joule per second. 1 joule per second. Right? So number of photons per second would be How much? 1 over this 19 photons per second will be there. So 1 over answer would be your 3.169 into 10 raised to 18 photons per second. Now one photon creates one electron hole pair. So one photon translates to one electron hole pair. Fine. So one photon would be your sample this one electron hole pair. Okay, and this is for your entire sample, right? This is for your entire sample, this 1 watt power. Okay, now they are asked, we have been asked that to find out number of EHP, determine the number of electron hole pair that are generated per unit volume per unit time. So per unit time we know, so per unit volume we just have to divide it by volume. Okay, per unit time per unit volume will be nothing but 3.169. What is the volume, by the way? Volume is equal to area into thickness, that is 1 centimeter square into 0.1 centimeter, that is 0.1 centimeter cube. Okay, 3.169 to 10 to the power 18 over, this is photons per second over 0.1 centimeter cube, that is 3.169 into 10 to the power 19 centimeter cube second inverse. Okay, so A is your right answer. Okay, so this is how you solve this kind of problems. Okay, so let me just see if I have time to do this. Under this dimension location. I think we can solve this, or you want to close the session here, or if you have any question.
So you can solve this problem.
Okay, fine, good. Okay, it is mentioned that an intrinsic silicon wafer is doped with these donors. Okay, that means your ND is given as 10 to the power 16 centimeter cube. 10 to the power 12 photons per second light is irradiated in silicon per centimeter cube volume. Assume each photon generates electron hole pair. Okay, so let me assume that this is my N0. Okay, N0 means electron concentration at equilibrium. So your N0 is 10 to the power 16 centimeter cube. So what will be your P0? This is power. Okay, Ni square over N0, that is your 10 raised to 20 over 10 raised to 16, that will be 10 to the power 4 centimeter cube. Okay, now suppose light is incident on the silicon slab. Okay, then what happens? Excess electrons generates, excess holes generate, because it will create in pairs, so number of excess electrons and number of excess holes will be same, and it is how much? It is 10 to the power 12. Okay, this number of photons per second light. Okay, that means this number of electron hole pairs are getting generated each second. So what is now your N? N is nothing but your N0 plus delta N, that is what? 10 to the power 16 plus 10 to the power 12 per centimeter cube. Can anyone try to comment what is this value will be?
10 power 16.
10 power 16, right? Because huge change in order. And what about your holes? 10 power 4
10 power
plus
12.
10 power 12. Okay. So you see the 10 power 12 centimeter cube. So by just looking at this, can you tell me that which carrier concentration will is have a larger impact upon these excess carriers due to these excess carriers?
Whole concentration.
Whole concentration, right? So what happens when this concentration of certain carriers right have risen suddenly? That means if suppose there are 10 to the power 4 electrons at this place, okay, suddenly it has become 10 to the power 12. So that means it will start to diffuse. That means your minority carrier, understand this very carefully, minority carrier change due to excess carriers are much larger than majority carrier changes. That means your minority carrier will try to diffuse and contribute to the diffusion current. Okay. So it is not the majority carriers but the minority carriers which contribute to your diffusion current. Okay. So now you know your N and P. Fine. Now it is asked that under this light emission location of the Fermi level. Okay. So just tell me one thing. N, can you tell me what is it respect to Ni? Okay, just no, don't need to tell me that. You can compute it from this. Okay. Minus EC minus EF over KT. You know this formula, right? So what is Ni? Ni is same NC exponential minus EC minus EI over KT. So if you just divide N over Ni, what will you get? You will get exponential minus EI minus EF over KT. I have just divided this by this. Fine. So your N is equal to Ni exponential minus EI minus EF over KT. Fine. So N you know, N over Ni you know. What was your N? N was your 10 to the power 16. What was your Ni? Ni was 10 to the power 10. Fine. So your EI minus EF would be what? Or let me say in this way. Let me do it step by step only. So from this expression, you can write this, right? EF minus EI over KT is equal to ln N over Ni, right? So your EF minus EI would be what? KT ln N over Ni. So KT was what? KT was 0.026, right? 26 millivolt. And KT is milli electron volt into ln 10 to the power 16 over 10 to the power 10. So if you calculate, it will come out to be around 0.36 electron volt. Okay. Similarly, if I follow the same argument, then my P of this will become, or I should say EF EI minus EF. Okay, just let me mention here one point that this does not remain EF, right? It will shift. It becomes your quasi Fermi level. This term is called quasi Fermi level That means it is not in equilibrium, okay? Quasi-Fermi level of electrons. Similarly, if it is EI and EFP, you can simply compute it as KT ln your 10 to the power 12 over 10 to the power 10, right? So KT would be your 0.026 into ln 10 to the power 2, and it will be nothing but 0.12 electron volt. Okay, so this is your for holes, this is your for electrons. So your answer would be B. Okay, so in this way you can compute the difference of energy levels. See, all you need to know is that your this carrier statistics equation, one equation you need to know. Even if you do not remember, you can compute it using that integration, the last problem number 10 what we have discussed. Okay, so okay, just let me stop here. These last 4 problems I will discuss next class. Okay, it is better to have some overlap between last lecture and this lecture. So if you have any question, you
Okay.
can ask. Okay, I think that's all for today.
Okay.
Okay, thank you everyone.